I made the picture so you could see what's happening here. So you have a hammer and bell concession. So this is the hammer and bell concession. So this person's going to take the hammer, come down, hit, and then this metal piece is going to go up. All right? And what they usually do is they damp this board right here so that a lot of the energy is basically lost in going from there to the energy that sends this thing up to make it more challenging. Because it would be very easy if this thing wasn't damped and didn't absorb a lot of the energy from the hammer. It would be very easy. Everybody would be hitting the bell. But they damp it so that it makes it very hard to get this metal piece up to hit the bell. So it says in the problem. So we have at a carnival, a hammer and bell concession uses a 9-kilogram hammer and a 0.4 kilogram sliding metal piece to strike a bell that's located 5 meters above the ground. Now, I know on the picture it says 6, but that's because I just copied it off of the problem that was on the test, and it had 6, so don't worry about that. Suppose that 25% of the hammer's kinetic energy is used to do the work of sending the metal piece upward. So that's where the substitution is made. Where it says work in my equation, so the equation is going to be for the metal piece. I'm not doing an energy equation for the hammer. 25% of the hammer's energy is going to now be the work that sends this up. Now the work is only happening from there to about there, because at that point the metal piece will leave this ramp and go up into the air. Also, there's friction. So as soon as, even right here, there's friction all the way up. So they give me that amount. I remember this problem originally just gave me the work due to friction, where you didn't have to write F times D. But knowing the force, I am going to have to write the force times distance for that. And then the question is, how fast must the hammer be moving when it strikes the lever so that the bell just barely rings? So for it to just barely ring, we want it so that it reaches its maximum height right at the point that it hits the bell. Because if it hits it with a speed, then that means I could have actually moved the hammer at even a slower speed. So we want the velocity so that it just barely hits the bell. So we're going to write our equation, and like I said, we're writing it for the metal piece. So we have KO plus UO plus W. Now, remember I told you there's 2 W's. There's the work that's due to the hammer, and then there's the work that's due to friction. Now, the work due to friction is going to be negative work, but I can either I can write this as a negative here, or I can just, when I write friction, I can put it in as a negative. One or the other. So you can either write a negative right there, but then you have to remember to not put a negative for friction, or just write 10 newtons as a negative later on. So you've got that, and that's going to equal KF plus UF. And just like every problem that when you're doing these, we want to first make the things that are 0, because there's usually something that's 0. And what can you tell me that's 0 in this problem? Original potential energy, because it's at its low point at the bottom, so we know that the original potential energy is 0. What else is 0? What's that? KO is also 0 because it's not moving until the hammer hits it, so it's 0 there. So we know that's 0. There's one other thing that's 0. What else is 0? KF, because we said this is going to go up, slow down, slow down, slow down, reach its maximum height, and then come back down so that it barely hits. So the final kinetic energy is 0. And my substitution, it says that 25% of the hammer's kinetic energy is used to do the work of sending the metal piece upwards. So I am going to be replacing this with 25% of the kinetic energy from the hammer. So that is going to be replaced right there. Now 25%, I can leave it as 0.25, or if you want, you can write that as a fraction. What is 25% as a fraction? 1/4. So if I want, I can write this as 1/4 because 0.25, I know the formula for kinetic energy is 1/2 mv squared. So I can write 1/2 times 1/4 would be what? What is it? 1/8. So I can write 1/8 mass of the hammer, velocity of the hammer, squared. So that right there is going to replace the work from the hammer. And the 1/8 comes from 1/4 times 1/2. There's the 1/4, and the formula for kinetic energy is 1/2 mv squared. So 1/2 times 1/4 gives me 1/8. The reason why I would do that is because then I can just multiply everything by the least common denominator to get rid of fractions. You don't have to do it that way. You can leave 0.25. And I know that the other problem was 0.40, right? So 0.40 is 2/5. So that other problem we did before, you could have converted, instead of use 0.40, you could have used 2/5 for that one. The problem is, what if this was 29%? What if this is 0.29 instead of 0.25? Well, there's not an easy fraction for that. I mean, I could write it as 29 over 100. All right, you could write it as 29 over 100 times 1/2 would be 29 over 200, and then just multiply everything by 200. So if it's not like a pretty percent that converts into a small fraction, then you can still write it as a fraction if you want, but if you don't want to, you can just leave it. For example, let's say if that was 0.29. Well, 0.29 times 1/2 would then be like 0.145. So you could just leave 0.145 in the answer. I don't care how you do it. There's a number of different ways that you can do that. So we're going to get, so that's the first one. And then because they didn't give me the work due to friction, but the force due to friction, I am going to write this as plus friction times D equals UF is going to be written as mg times the final height. Does everybody follow me to here? And notice I have not yet dealt with the fact that the friction is a negative. I could have put a negative there, but I haven't done it yet. So that means that when I do plug in, I'm actually going to use negative 10 newtons. If I don't want to remember that, I could have made a negative right there. So now the unknown in the problem is the velocity of the hammer. So first thing I'm going to do is I'm going to get rid of the fraction by multiplying by the least common denominator. That's going to distribute the 8 to every term. Then I'm going to move this to the other side, and then I'll divide by mh and take the square root. So I'll do it in a couple steps. So the first thing I'm going to do is multiply everything by 8. So I'm going to get mh vh squared plus 8fd equals 8mghf. Now notice that one of my m's has a subscript and the other one doesn't. If you want, you could put M for metal piece, like I could put an M there. But I am distinguishing this mass as being different from that mass. So I use a subscript here. So that's the mass of the hammer. This is the mass of the metal piece, because our equation is an equation for what's happening to the metal piece. So I don't care. You can, like I said, you could put an M there also to distinguish it from that. So the next step, we're done with the physics. The rest is just algebra. So I want to get the velocity of the hammer by itself. So like I said, I'm going to move this term to the other side, and then I'm going to divide by that, and then I'm going to take the square root. So when all is said and done, we're going to have 8mghf minus 8fd over the mass of the hammer. Does everybody follow what I did there, the algebra? Now you can almost tell here that I'm going to need a negative there, because I know that if there's friction, the hammer has to swing faster to overcome friction than without friction. So this part of the problem is the amount that I have to swing it with a greater speed to overcome the fact that friction is going to continually be reducing the energy that I have as soon as the metal piece leaves the ramp, leaves the lever. So we'll plug in the numbers. So the velocity of the hammer is going to be the square root of 8 mg h minus 8 fd. Now, I know some people, there's an 8 here, and they'll like factor out the, it actually is easy to put in your calculator, leaving it like this. Just because it's an 8 in both of them, just keep it in both of them. And so that's going to be divided by the mass of the hammer. So the mass, this mass right here is the mass of the metal piece, and that was what, 0.4 kilograms? So 0.4 kilograms, that's 9.8 meters per second squared. The height, what's the height in the problem? It was 5. Okay, yeah, it's different than that number, so it's 5. And here's where I have to remember that I have not yet put the negative in. It was negative work, and I didn't make a negative. I didn't make a negative up here. So now is where I do have to put it in here. So instead of 10 newtons, I'm going to put this in as negative 10 newtons. And what's the D? Yeah, it's also 5 because it's happening over the entire time. From start to finish, friction is happening from the beginning until the end. And then the mass of the hammer was 9 kilograms. So as far as units canceling, the kilogram would cancel the kilogram would cancel the kilogram, and I'm going to have meters squared per second squared under a square root. So mathematically, that's going to give me meters per second. And same thing here. Remember, Newton is really a kilogram meter per second squared. So the kilogram part of that would cancel, and I'd have meter per second squared times meter. So mathematically, it does give us meters per second. And if you solve this, I think it came out to 7.87. All right, and that is